topic. We are going to discuss about the composite, how to model the composite, and how the damping play the role, and how you can take into account while modeling it in finite element framework. Okay. Fine. See, when we are going for a dynamic analysis means vibration analysis, where you have that equation mx dot plus cx dot plus kx. Basically, we are going to solve this equation. Dynamic equation basically mx double dot plus cx dot plus kx is equal to f. That equation is normally solved. Okay. Now f here is the forcing function of the time. And when we go for our static testing, for example, our cube test, cylinder test in our laboratory, we will observe that we are solving that kx is equal to f, that equation. Okay. In that case, static test is in the sense that we normally get the information from the student that static tests are those tests in which load is constant. Basically, whenever I ask the question to the student, they used to reply in that way, that whenever load is constant, that is our static case. But we will observe in the laboratory, whenever we do cube test or the cylinder test, we normally gradually increase the load. So gradually increase the load means it can be increasing in a linear fashion or it may be a smooth fashion. Basically, our intention normally used to be apply the load and gradually increase the load without causing any vibration to the system. Okay. So those are saying that static tests are those tests in which load is constant. They are perhaps theoretically correct, but when you are go for practical application, in that case, with a constant load, we may not be able to do the testing. In that case, we need to increase the load. Okay, but again, we need to increase in such a fashion that that forcing function, that force, do not cause any acceleration to the system. So any acceleration in the sense, if there is no acceleration to the system, then mass into acceleration, that component, that also is a forcing component. Here you can see that in that equation, here you can see in this equation, right side we have the forcing function of force. So m minus x dot must be a force, c times velocity must be a force, k times x must be a force. Okay. Now, when you talk about the static analysis, in that sense, we are saying that load should be such that forcing function or for load will not cause any acceleration to the system. If there is no acceleration to the system, in that case, change in acceleration, or sorry, if there is no acceleration to the system, then this component will be zero or very negligible. C times x dot also should be zero or negligible. Okay, in that case, we will observe that we normally solve that k x, which is a function, k x, which is a function of t, that is equal to forcing function, which is also function of time. Okay, so here you can see that we are solving the equation where x and force, which is displacement and the force, both are the function of time. Okay, so those are saying that static tests are those tests in which load is constant. That you can say theoretically correct. Okay, but if you go to the practical application, in that case, force as well as displacement normally is a function of time, but forcing function is such that it does not causes any acceleration to the system. In such test, we normally say that is your quasi-static testing. Quasi-static testing, or very frequently used to say static testing. Now that is our static analysis. Now whenever we go for dynamic analysis, in that case, whenever we go for dynamic analysis, in that case, we normally solve this equation mx double dot plus cx dot plus kx is equal to force. Okay. So here you can see all are the function of the time. Now, when you go for dynamic analysis with respect to our time, in that case, we'll observe that we normally get a response like this. Maybe somehow periodic, again, there will be something like that. Okay. Now, what happens if you change something, if you if there is some damages in the structure, if there is some changes in the damping, if there is some changes in the K matrix, or there is some changes in the mass matrix, all the cases will observe that the changing in the response is almost very similar in nature. Okay. In that case, we'll observe that it is very difficult to identify which is basically causing the change in the response. For the damping, we know that if damping is there, if damping increases or decreases, you'll observe only the peak part. This part maybe go up and down, okay, but rest of the cases, for otherwise, if we consider the mass and stiffness case, you'll observe that changes in this response will be very similar in nature. Okay. So now what happens if you do the testing in time domain, you will observe it is very difficult to identify which basically causing the change in the response. Okay, for the same reason, what we used to do, we used to go for dynamic analysis in our frequency domain, Now, what is the benefit of going for the frequency domain analysis? You will observe that we are getting very well-defined pattern if we change this time domain response into the frequency domain response. Okay. Now, what happened? How to do this transformations from time domain to frequency domain? We can do the F50 of it. Okay, so if you observe that in MATLAB or in any standard software, they can directly do the F50 for you, and you can get the response from time domain data to the frequency domain data. Okay, so here we'll observe that if we do the testing, here you can see this is the one type of response in the frequency domain. Frequency domain, how you identify whether the response is time domain or the frequency domain, will observe about the x-axis. If the x-axis represent time, then basically you are doing the analysis in time domain. If x-axis is in the frequency, if in the x-axis there is frequency, that indicate that you are doing frequency domain analysis. Okay. Now in the frequency domain analysis, if basically what we used to do, we used to convert time domain data into the frequency domain by doing the F50 of it. There is other method also, model superposition method also is there. From that also we can do that analysis. Okay, we'll see how we can do that. Here what you can do, here what you can observe, here you can observe that in the frequency domain analysis we have a well-defined pattern. Now, how to identify that which basically parameter influencing that response? Here you also observe that if this peak, this is the peak, okay. If this peak is very sharp, okay, if this peak is very sharp, then you can identify, you can say that basically that is causing to the change in the damping parameter. If this peak is sharp or blunt, both the cases will observe that is due to the change in the damping parameter. Okay. If there is change in the damping parameter, then this peak will be in the same position, only this magnitude will change. Okay. Now, if there is some changes in the mass or in the stiffness, you will observe this peak is basically shifting this side or this side, depending on how mass and basically stiffness playing the role. Similarly, here also you can get some shift in the x-axis. Basically, x-axis means in the frequency. From that, you basically identify, okay, if you have the data in the frequency domain, in that case, you will have well-defined pattern, and from the pattern you can identify. Because here you can see what we have done here. You can see that actually here there's two graphs. One is your FRF experimental graph. We initially capture the data through accelerometer. Here also you will observe in the dynamic analysis we normally use accelerometer. Okay, so accelerometer, what accelerometer is to do? Accelerometer is to capture the acceleration. Okay, from the name accelerometer you can also identify. Accelerometer basically capture the acceleration. So how is to do that experimental testing? If you have a beam sample like this, or if you have a plate sample like this, what we should do is to put our accelerometer, okay, and we should do hammering in some particular position here or in the plate somewhere like that. Okay, so what we should do is to discretize the whole beam into two number of segment, and we place the accelerator at one position, and then we should do the hammering here, here, here like that. Okay, for the plate also we to discretize whole plate into few number of segment, and we normally place the accelerator at one location and then basically hitting the plate in different location, and we used to capture the acceleration through the accelerometer. Okay, now again accelerometer also can be two types. One is the 1D acceleration. Okay, while if you do that, if you used to go for real life testing, in that case you also make sure that what is the type of accelerometer. Accelerometer maybe 1D means one directional measurement it can do. So here how we are placing the accelerometer, that also matters. For example, if you have accelerometer which can measure only in the one direction, means vertical direction, then you should place the acceleration in vertical direction only. You should not place in other way. You should not place this way. Otherwise, your measurement will be wrong. Okay. Now, if you have the 3D accelerometer, in that sense, the accelerometer can measure along X, along Y, along Z. So in that case, you will not have that issue. Okay. But you will observe most of the cases we used to have 1D accelerometer, that is less cost, and normally we used to have if you purchase any dynamic testing instrument. Okay. So what we used to do, we used to basically displace the whole plate or whole beam, and we place our accelerometer and we hit it and we measure the acceleration. Okay, so the acceleration, again accessing what we will get acceleration means we'll get the again time domain data with respect to acceleration. Here we'll have acceleration and here we have time. Okay, so again we'll have that type of pattern. Okay, like this. Now what we normally do, we ask that software, basically that dynamic testing instrument also comes with that uh, all the software necessary to convert your time domain data into frequency domain data. Okay. So what is to do? It is to convert the data into frequency domain, and it will get the frequency domain data in this way. So here we get our experimental data. Okay. Now here you just see we get the numerical data. Okay, so when you convert the time domain data into frequency domain data, that time we used to say the frequency response function. Initially, we used to have acceleration. Now we have, after doing the FFT of the time domain data, we get that FRF, frequency response function. Now here you can see that our peak is coming one by one. Okay, but if you do real testing, you'll observe that initially initially both the peak will not come one by one. If anyone did some experiment, if anyone in dynamics did some experiment, yes. Okay. If anyone do some experiment in a laboratory, in dynamic testing in laboratory, you'll observe that experimental FRF may go like this, and numerical FRF may go somehow like this. Okay, in that case, we'll observe there is a shift in the frequency domain. So here in our experimental case and numerical case, what you will get, you will observe that we are getting experimental frequency like this. Okay, and this one may be your numerical frequency. Numerical frequency means which you are getting through some numerical analysis in MATLAB or through some software. Okay, now problem will be there that will be there that there is some shift in the frequency, as well as there is a change in the damping. Okay, now how to deal with that? Because if we do the experiment, our FRF will be like this, and if we do the numerical modeling, our FRF will be different. But those the pattern will be similar, but you'll observe that there is a shift in the frequency. There is shift in the frequency. Okay. Now how to deal with this such situation? Here what we can do, you can basically do some updating things. So what you can do, you can do the updating in numerical in a manual way. Okay, you can do this updating in a manual way. Manual way, how we can do that? Now again, now come to the composite part. If you have a composite plate like this, okay, in the composite, probably you know that in the composite you used to have E1, E2, G12, and then you can have percentage 1, 2, then we can have 1, 3, percentage 2, 3, again G2, 3, and G1, 3. So like this, we'll have total, then it will be E3. Total, there will be total 9 parameters. 3 parameters from the Young modulus, 3 parameters from the shear modulus, and 3 parameters from the Poisson ratio. Okay. Now, Now problem will be there that I'm going to discuss. Okay. So now if you have a plate like this, okay, and if you have different pattern in that FRF, what you can do now? Basically, you can update the mass or stiffness so that you can basically you can basically try to get the frequency one by one. Okay. So here we have to go for updating using some model updating technique. Either you can use generic algorithms or you can use gradient based method. You can use any other updating technique to update the parameter. Okay, so here what we can update? We can update the mass or we can update the K. K in the sense we can update your E's and Poisson ratios. Okay, all three parameters we can, all three means total 9 parameter we can update. Okay, now problem is lying here with the mass and the K. Here also you know that omega is equal to root under K by M. Okay. So either you can update mass or you can update the K. Both will give you the same result. Okay. So now which parameter we should consider? Here you can see that omega is equal to root under K by M means you can update the mass or you can update the K. Both which will lead to the same result. Okay. Now here you have to do some observations. Observation is that mass basically we can measure, the density we can measure, right? Because if you have a plate or beam, any sample, if you know, then you can basically measure the length, you can measure the width, or you can measure thickness. From that, you can get the volume, and if you measure the weight, from that you can basically calculate the density. So mass parameter you can basically calculate very accurately. If you have good weighing machines, you can calculate the mass very accurately. Okay, so now there is no need to update the mass. You can keep the mass as a constant. Okay, now you can update the stiffness, or other way you can update the E value, G value, and the Poisson ratio, and you can basically match our response. Response in the sense you can basically get the response which basically lead to the which basically you can basically land up to this type of solution where you will have the peak in the same location, only the magnitude of the peak will differ. Okay, next what you can do, so in the first step what you observe that we will ignore the updating of the mass because we can measure the mass accurately. In the second step, so we can measure the only the E value, G value, or Poisson ratio, so that we can basically update the frequencies. Okay, so once you update the frequency, next job will be to update the damping parameter. Okay, if you update the damping parameter, you will observe that we are getting very well matched frequency, well matched FRF. Okay, so now if you update both stiffness in the sense E values, G value, and Poisson ratio, and if you update the damping, you'll observe that your FRF response is matching very well. So this way basically we can deal with our uh, model analysis problem. Okay. Now problem lies how basically we can update the stiffness. Okay, how we can update the stiffness. So in the K is the stiffness. So in the K, you'll observe that we used to have a E1, E2, E3, all three parameters. Then we have G1, 2, G2, 3, G1, 3, and we have Poisson ratio 1, 2, 2, 3, and something like 9 parameter. Okay. Now again, if you do some sensitivity analysis or if you change the parameter, if you change this parameter a little bit, this parameter a little bit, you'll observe that this Poisson ratio does not affect the frequency in a greater way. If we change the Poisson ratio only 50% also, we'll observe the frequency is not changing. So what it indicates? It indicates that Poisson ratio is not an effective parameter to update our frequency or to update the K. Okay. So whatever the testing value you are getting in the experiment, you can assume the same test value for the Poisson ratio. Okay. Now you will observe that if you're using a plate which is basically uh, TFRP, or that your simple plate, okay, simple plate which you are modeling using your equivalency layer theory. In that case, you will observe that our E3 and the parameter related to three reactions is this three parameter does not have a effective rule. Okay. So what we get again now, if you have a plate which is very thin in the sense, uh, thin in the sense it is have of 2 mm, 5 mm, 10 mm like thin plate. In that case, we'll observe that E3, G13 and G23, G13, G23 do not have big role there. Okay. Now to get that our updated stiffness, you'll observe that only three parameters E1, E2, and G12. These three parameters play a big role in the updating of your E value. Okay. So here, what we observe that we have this equation. Okay. And we're going for dynamic analysis. We got one response from the experimental data, and we have another response from our FEM data. Okay. Then what do we observe? We observe that there is a big difference between experimental observation and our FEM observation, FEM modeling. Okay. Now, next what we did, we observed that omega, the frequency, is basically root under K by M, and mass we can measure very accurately. So what we are going to do, we are going to play with the K so that our experimental omega and numerical omega matching very well. Okay. Now in the K, we have effective three parameters E1, E2, and G12. These three parameters, if you update, you will observe you can update our K very well. Once you update the K, basically we will observe our omega experimental and omega numerical will match very well. Okay, now if we have omega experimental and omega numerical matches very well, you will observe that we are getting a response like this in the frequency. We are getting a response like this in the frequency domain, where we have some difference in the damping. Okay, but our our peak are coming almost in the same location. Okay, now what we can do? Now we will go for updating the damping. Now again, damping in composite can be defined. A different researcher try to model the damping in different way. Okay, many people measure the damping in as a viscoelastic damping, and many cases we can measure as your viscous damping. Okay. Now, if you go for viscoelastic damping, now what is going to happen? If you go for viscoelastic damping, you will observe that our solution we are getting as your complex term. E in that case, you will observe E is equal to E real plus E imaginary. Okay. Now, if you have a E which is a complex term, then as an engineer, we will feel very difficulty to model it. Okay. So for the same reason, many people try to model it as a viscous damping, and it has been observed that viscous damping also showing good result in the case of dynamic analysis of a composite. Okay. So now if you go for viscous damping, again can be viscous damping can be two types. Okay. Viscous damping again can be two types. One is proportional damping, another is non-proportional damping. So what is the proportional means? Viscous damping is proportional, means damping is basically proportional to the velocity. If this damping is proportional to the velocity, then we can say is a proportional damping. If the damping is not proportional to the velocity, then we can say non-proportional damping. Okay. Now again, in the proportional damping, which there is two type of modeling. One is Rayleigh damping. Rayleigh damping basically we can observe that damping we normally write in terms of alpha m plus beta k. Okay, alpha m plus beta k. So whatever the phenomena is occurring for the damping, we normally associate the damping with the mass and the stiffness. Okay, so you'll observe this Rayleigh damping. Rayleigh proposed this damping nearly almost 100 years back, nearly 1827 in that time. Almost 100 years back, he proposed this type of damping. That basically you can say that before 100 years, Rayleigh realized that if we try to model the damping considering all phenomena which is basically affecting the response, it will be very difficult to model, because damping can be affected by the damages or some hole or some crack. Damping also can be affected by the shape. You can see that our bell in our temple. It has some particular shape, and in that particular shape, we still have high amount of pitches. Means in that case, damping is low. If there is some crack in the bell, you will observe we are getting some different type sound. Basically, that indicate that there is some damages or some crack in the bell. So, shape as well as crack as well as the material, all parameters play a big role. Not only material, how in which basically in which environment that the structure is lying, that also play a big role. Basically, interaction between the medium also play a big role. So what really observe that if you try to model the damping considering all phenomena which affect the damping, it is very difficult to model it. Okay, so what he proposed a very simple model. He said, let's assume the damping basically affected by the mass and stiffness, or you can model the damping in terms of mass and stiffness by considering the two term alpha m plus beta k. Okay, now what is our role now? Our role will be to update alpha and the beta because already you have updated mass, updated mass in the sense we can measure the mass accurately. So we kept that mass there. We have updated our E value, E1, E2, and the G12. Okay, and we get our K value with some good accuracy. Now what we're going to do, we're going to update mass, we're going to update alpha and this beta term so that we can model the damping quite accurately. And if we update this damping parameter, we'll observe that our response is basically matching very well. So here you can see after updating all parameters, after updating E values and after updating the damping, you observe our response is matching very well. So this way basically you should deal with whenever you are dealing with the vibration analysis. Okay, so here what is our assumptions? Our assumption is that our damping is our proportional damping, Rayleigh damping. Okay, apart from that, we do not have such other assumptions. Okay. Now, while doing this type of vibration analysis and in modeling, again, you need to take care of the boundary conditions. Many people use the boundary conditions as a simply supported. Okay, simply boundary conditions, simply supported in the sense it is basically lying as a simply on that support. But whenever we go for the testing, you'll observe that if you do the hammering, if you give the impact, that the structure is not lying on that particular position. It may also vibrate and may be lifted from the support. So really, that you can say ideal symptoms of it is very difficult to achieve the ideally simply supported conditions, and really doing the simple supported analysis is very difficult in our experimental case. So what we should do, we should go for either free conditions, free in the sense how to achieve the free conditions. We can take some rubber band, the simply rubber band, what you basically can get from the market. So here you can see from the picture that this is the rubber band. This is the simple rubber band, okay, that we can get from the market. Basically, you can have to see that the rubber band should be good enough to take this load. Okay, you can take the rubber band and place the sample on the rubber band and do the testing. Okay, so this way basically we can achieve the free. So now again you may say, sir, this is not now really free. So you will observe that stiffness of this plate of the structure and stiffness of the rubber, if you compare, it is basically huge difference in the stiffness. Okay, so this elastic band will not affect your response in a greater way. Okay. So this way basically we can achieve the free conditions. Other conditions you can go for, that is a fixed conditions. So how to achieve the fixed conditions? You can basically use some C clamp to fix it, and then you can put some load over it. That also you can achieve our fixed conditions. Okay, so if you go for dynamic analysis in your laboratory to do your research, in that case either you should go for free conditions or you should go for fixed conditions or cantilever conditions. Okay, this is basically you can have good accuracy in your experimental data. Okay, since in the fixed conditions we do not have any other motions, that means all are fixed. All means your acceleration along x direction, acceleration along the y direction, and z direction all are zero. So do not have any other assumptions there. In the simply supported conditions, we have to assume that it is only fixed up in the vertical direction, not fixed in this direction. It can slide this direction, but it is very difficult to achieve practically. Okay, so if you go for any analysis in the dynamic domain or for vibration analysis, you should go for either free or fixed frequency if possible. Okay, and if you are forced to do simple simulated conditions, then you have to take proper precaution and you have to make sure that is you are achieving the ideal simply separate conditions. This is basically you could go for dynamic analysis, and you should compare our response obtained from the dynamic uh, domain in the experimental data as well as the numerical data. Okay, so let me go for some discussion with you. Then again, we'll uh, come back to our topic. So, do you have any other queries here?
Uh, Subhajit sir, thank you.
Yes,
I have one question. In
yes,
this,
yes,
in the you're having this frequency response function, which is
yes,
obtained from the
yes.
experiment, and
Mm-hmm.
you are having a model. You are having a plate
Numerical model.
model simulation
Mm-hmm.
where you vary the Young's modulus and the mass of the system,
Mm-hmm.
and make sure
Mm-hmm.
that the frequencies match.
Matches.
Uh,
Yes, yes.
the question is that the actual plate, we can actually test the plate and we get the Young's modulus, and we can
Okay.
actually measure the mass of the plate and get the mass.
Mm-hmm.
So
Mm-hmm.
why are we why are you doing this inverse analysis to fit this?
Okay, okay. Now, I see if you go for composite material, it is heterogeneous in nature. Okay, if you go for steel testing, it may matches very well because it is isotopic in nature, and we know that steel GPA nearly 200 GPA, and we are doing model analysis means it is your linear analysis, so it may matches very well. Okay. Now, problem arise if you go for composite type of material because it's heterogeneous in nature. Now problem is that if you do the testing, uh, practically coupon that it should be really rectangular in nature, but practically achieving rectangular shape is very difficult. If you hold that sample and do the tensile test, sample may fail in the grip zone only. Okay, so there are a lot of issues there with the testing also. You may get some value which is very close to it, but you cannot achieve that almost same that with the same accuracy we get for the still testing. Okay, so again E1 and E2 you can get, but G1 2 though we have some guidelines as per ASTM standard. In that case, you need to go for 45-degree angle sample, and then you have to do the testing, and then again you have to correlate with the E1, E2. Like that, you basically get the G1 2. Now that equation also will not exactly correct. You can get some value. It may be will give you the accuracy up to 80% or 75% like that for the G1 2. Okay. So now again the accuracy of the G1 2 also rely how well you basically got the value of E1 and E2. Okay. So these parameters are there. If you go for testing for composite metal, then you have to take care of this all these cases. Because
Suppose
if you do that,
if
yes.
if you actually test the material and have some some Young's modulus and mass values, we can
Okay.
start from there. We can start the
You can
simulation from
start
there,
from there,
and yeah,
and actually, what are many cases,
shear parameters.
what a student needs to do, what are the some students to do the in clever way. Mm, say they used to do the testing in our in laboratory, and whatever the E value value they're getting, they put the direct value to that our FU modeling, and what are the frequency they're getting, they used to claim that is the experimental frequency also.
Okay.
But
Okay.
that is not a good practice
No,
for
yeah,
some
that is wrong.
that is wrong. So you should go, but experiment is the real. You should not deviate from that. That is the real thing you are observing. Okay. Now you
Yeah.
can play the role with the numerical modeling, FU modeling. Okay. So now in the FU modeling again, you can have our cell modeling. You can have solid plate modeling. Uh, okay, so again, you have to think that which type of modeling you should choose. Okay, that I'm going to discuss next. So I want to discuss with the students, with the participants, to see how much they are acquainted with this discussion. Then only I can jump to our modeling
Yeah,
part in how to model.
yeah.
What are the difficulties there in the modeling also, and how can deal with that. So do you have
Yeah,
any
it's
other
very useful,
queries?
sir. You can continue, I think. Yeah.
Okay. No, if anyone has the queries, so we can discuss with them, and then we can proceed. Is there any queries?
Participants can,
Yeah, yeah.
if you
I'm
have
actually
any questions, you can ask, sir.
yes.
Uh, Shilpa madam, you
So
can ask any questions, or Arya, Shilpa madam, you can ask.
Yes,
If you
sir.
have,
Yes, sir.
yeah.
if you have any queries, you can ask, sir.
No curious, sir.
Okay,
Okay,
fine.
fine. So now what we're going to do, we are going to see how we can model a composite in our standard software. So you see this part also I to discuss in our MTech classes. Okay, so I also create some video on it, and I to share in our to our student who is to come to my class, laboratory class. And basically what I should do, I used to give some brief discussion about the problem, and then I share that link to them, and they used to observe it and they used to model it in the same way I used to do. Okay. So what we can do in in our standard software, the standard software basically you'll observe that it has to have few part in the sense, few steps. First step is that you have to create the geometry modeling of that structure. Then we have to define the material property. Then you have to define the boundary conditions. Then you have to see that how many discretization you want to do. Discretization means FEM in the finite element model. A finite element model means you have to discretize. You have to basically divide whole structure into finite number of element, and then you have to do the convergence study. You have to see that how many number of element is correct for you, how many number of element give you with a good result, and then you have to go for analysis. What type of analysis you want to perform? So first is your modeling of the geometry. Next is your modeling of the material, means what type of analysis or material means whatever material you are using. Basically, there you can give the input of E1, E2 if you are doing our elastic analysis. If you are going for nonlinear analysis, in that case you have to give some nonlinear property also, damage parameter also. So one is your modeling of the geometry, next is modeling of the material, next is your boundary conditions, next to you have your discretization of the material, and then you have to choose what type of analysis you want to perform. Okay, so if you decide all the things, then you can basically analyze a structure. Okay, so here what we are going to do, here we are going to create a model. Now here you can see we have 3D, 2D planar material. Again, we have shape, whether it is solid or cell. Okay, now composite also can be modeled as a solid element, also model as a cell element. Okay. As a beginner, you should not basically no need to go to cell modeling, because if you go for cell structure analysis of cell structure, you may land up with other complications. Complications in the sense that your analytical modeling of cell is very difficult. Okay. For the same reason, many people shifted to the numerical modeling for the cell. Now, in the cell element, what is do basically this is 2D type of model. In the cell, what we do, we to ignore the thickness. Ignore the thickness. We are ignoring the thickness in the modeling stage. Okay, not in the in a real problem, we are not actually ignoring the thickness. Thickness here we are consider 2D modeling, and then we assume that okay, there is some thickness, and we used to calculate all the things in the background, and then we basically analyze it. So one way is that modeling as 2D. Another one is the 3D. In the 3D element, basically in the 3D, you have to basically model as it is, as it look like. Okay, so now here, what we're going to do, we're going to go for cell model. Why you're going for cell model? Cell model normally very applicable, very suitable if the thickness is very low. Okay, again, low in the sense it is low in comparison to the length and the width of the breadth, you can say. Okay, if your length is in the range of your 300 mm, 400 mm, or 100 mm, and your width also in the range of your 100, 200, 300 in the range, and thickness is basically in the range of 10 mm, 5 mm, like that. In that case, you can go for cell element modeling using cell. Okay, if your thickness is very large, 20 mm, 50 mm, or in that range, in that case, you should go for solid element analysis. Okay, in that case, you should use solid element. So now here, what we're going to do, we're going to go for cell modeling here 3D is not playing, it is the modeling space. So in that it will show in your X, Y, Z coordinate, nothing else. Okay, so here actual modeling we're using as a cell modeling. So basically you can see only the 2D as a 2D. Okay, so now what we're going to do, we're going to consider that here you can see it is here you can see it is asking that enter the starting point. So here what you can do, you can keep 0, 0, and then if you define the other corner. Other corner here, what you can do, if you give that length and that breadth, what you can do, it is 0.400 mm means 0.4 or 0.3. So here you can play it like this. So again, whenever you are modeling it, what you should make sure, you should make sure about the unit. Okay. Many times what student is to do, they to make mistake in the unit systems. Okay, if you're providing that unit length unit as a meter, then your density should be kg per meter cube. If your unit system is mm, then you need to convert the all of the unit systems. Okay, if you're giving your length in meter system, then its stress also should be Newton per meter square. If you're giving that length in mm, then your stress also will be Newton by millimeter square. So student many times what they used to do, they used to basically mix that all the unit systems and they may land up something the wrong result. Okay. So here what we're going to do, we are going to we are basically created that modeling here. Modeling is geometric modeling we have done. Next what we're going to do, we are going to define the property. Here in the property, you just see we are providing the density. Since we are doing dynamic analysis, density is mandatory for us. So density is how much here, what density we can give? We can give just approximately 1300 kg per meter cube, and E we are providing at the approximate value. E we are providing a 30 GPa, 30 E9, and policy ratio you can write 1.17. Okay. Now here what we're doing, we're again selecting as a cell, and we're basically modeling as a homogeneous. And here it is asking about cell thickness. See, that was actually I was discussing. Though we are modeling as a 2D, we are not ignoring the thickness. We are calculating all the things based on the thickness here. So here we can see the coordinate thickness of 10 mm is 0.1. Okay. And like this. And here we are basically assigning the property here. So here you can see now its color changes from your white or gray color to the green color. So here it indicates basically we have defined the meter property correctly. Now this assembly part, there is nothing to worry. You can select assembly and create instance. Okay. And now here what we can do, we can go for meshing. Again, now why you go for cell analysis and instead of solid element analysis? Cell basically, if you consider 2D element, you'll observe that cell model is to give good accuracy with a few number of elements. That is another benefit we have by modeling using cell element. Okay, cell element can give you the good result with few number of elements. If you use solid element, in that case you need to use more number of elements, and it may take few more, maybe few times more, maybe 5 times, 100 times, 200 times more time with respect to cell element. Okay, so here what we are doing, since we are using cell element, so here instead of assembly, here we should use part here. Here what we are going to do, we are going to discretize here. So here what we are going to do, here we are going to giving the seed value in the sense basically we are creating the node here. Okay, so now here you can see we can create the node by considering edges, or you can define as a whole part. Okay, so but since we have the edges and while defining edges, what we can do, we can select the edges. So here you can use the shift button and mouse to select. Okay, now here what we're going to do, we're going to go for number. So in this direction, we are going to give 10 number. Okay, and other side, this edges, and again shift button and this side. And if you select now here, we can give 5 number element. Now this way basically we created the edges. Here you can see that the pink triangular is showing. This way basically we are creating the node there. Okay, now what we're going to do, we are going to mesh. This way basically we are creating the meshing or discretization of the element. Now again, accuracy of the FEM model also depend how well the shape is. Okay, so here the shape is very much rectangular in nature. If the shape is very close to our square, in that case FEM normally give good results. So here what we can do, we can discretize in finer way to get good accuracy. Okay, so but here we'll go with this one, and if we get if we want to do that our convergence study, then you can basically discretize in finer way. You can check it. Okay, so here basically we have done the meshing. Next, what we're going to do, we're going to define the boundary conditions. So boundary condition means here already I already informed you, either you can go for free or you can go for fixed conditions or cantilever case. So here we can go for free, okay, or you can go for cantilever. Here what you can do, here let me show you. So here we can have different type of boundary conditions. We have displacement type boundary conditions, n cluster bound. N cluster basically indicate the fixed conditions. So here what we can do, you can choose this one and consider n cluster. So basically you can see U1, U2, U3 all are 0, means there is no displacement in this edges. So whatever the nodes are there, in the node there is no displacement. Okay, all displacement, all rotation are 0. Okay, now what we can do, so we have defined the geometry, we have defined the property, we have defined that meshing, and we also define the boundary conditions. Now we need to go for an type of analysis. What type of analysis we want to perform? Okay, so here you can see, here we can go for linear perturbation. Whenever we want to go for dynamic analysis, okay, we need to select linear perturbation options. In the linear perturbation, you can see we have frequency analysis, we have backlink analysis. Those are interested in backlink analysis and frequency analysis, they should go for linear perturbations. Here, since we are interested in frequency domain analysis, here we are choosing frequency. Okay. Now here it is showing that what type of solver we want to use. Here we have Lamb-Coil solver, we have subspace solver, or we have AM solver. So Lamb-Coil subspace normally is to give the good result. Okay. Now here it is saying that what are the frequency ranges we are interested in. So here we can see that we can say all frequency, or you can say 10 number of frequency. Okay. And here you can see minimum frequency interest, all the things are there, but at this particular time, and that is not your interest. Here we are asking up to 5 or 10 frequencies, like that. Now we should go for submission. So here we will go for submissions, and now we are going to submit the job, and we are going to see is there any error or any error or warning. If you observe some error or the warning, we need to rectify it. We need to correct it. Okay, then you need to submit. Okay, so here it is showing the status is running. Basically, it is taking the model. Here you can see it is showing that analysis input file completed successfully. Okay, it is job 1 completed successfully. Here also you can see job is completed successfully, means there is no error or no warning. Now you can go for the result. Here you can see that our mode shapes. Okay, this is basically first frequency, first mode shape is bending type of mode shape it is showing. Okay, here you can see in this way. I'll go for this one. Here you can see both edges are twisting. Okay, there is also one bending type of model, bending mode you are getting, and here some that your in plane bending is basically it is twisting like this. So in plane bending is there. This one was your out of plane bending, but this one is in plane bending. Okay, this is also one type of torsional mode is coming. So this way basically you can model, you can get the frequency. Okay, now how to get the FRF? For the FRF, you need to go through my video. I will give you the link. Okay, I'll share the link to share, and you can get the link from there. So for the FRF, what you can do, here, what you do after doing this this step, you have in the second steps, you need to give one unit force and then you have to run it again, and again you have to define what are the frequency range you are interested in, and if you run it, you will also observe that FRF there. Okay, so this way basically you can go for dynamic analysis. The first step is there. You go for dynamic analysis and first identify the experiment in the laboratory, and then you come back to our FEM modeling, and then you try to see whether your experimental frequency and that FEM frequency is matching or not. Okay, if this is matching is fine, then also you should doubt why it is directly matching, because there are a lot of constraints are there in the experiment. There can be slippage in the bond, there can be imperfection in the sample, there can be failure in the grip zone. Okay, so there are a lot of factors for which you may get some slight changes, slight error in the E value. So you need to make sure that you are getting good E value while measuring, while doing the experiment, and you should give same E value in the FEM modeling. While modeling the FEM, you also should be very consistent with the unit systems. My suggestion is that you should go for Newton meter unit, so that you whatever the value you are getting, that will come as it is. So all the stress will be Newton meter. And later on you can convert into MPa Pascal. You are getting Pascal, so you can convert, just multiply with the 10 to the power 6, you can convert to the megapascal, means Newton per mm. So this way basically you can do in simplest way. Okay, so our time is almost over. If you have any queries, please let me know.
Participants, if we
Yes.
we have any questions on abacus modeling, you can
You
ask
observe that
now.
in our class, I normally, those who attended my class, they know that very peacefully we used to deal this thing, because earlier what I observed that those students are attending the class FEM modeling, they are facing the issue in the abacus, and a lot of issues they're facing. So I, as a single teacher, I face very difficulty to handle nearly 100 students. So what I did, I basically model it,